Alright, so in this video I'm gonna be explaining another important article about domain adaptation, still in the unsupervised setting, and the task that we want to do is joint information extraction. Information extraction, for example, event extraction, relation extraction, entities. So I'm gonna be explaining this paper in 2022 that uses this idea of domain adaptation for training, domain adversarial training of neural networks. Joint information extraction aims to jointly solve multiple tasks in the information extraction pipeline. Entity mention, event trigger, relation, and event argument extraction. Due to their ability to leverage task dependencies and avoid error propagation, joint event extraction models have presented state-of-the-art performance for different information extraction tasks. However, an issue with current joint information extraction methods is that they only focus on standard supervised learning setting, where training and test data comes from the same domain. Cross-domain or domain adaptation learning with training and tests in different domains have not been explored for joint information extraction, thus hindering the application of this technology to different domains in practice. To address this issue, our work introduces the first study to evaluate performance of joint information extraction models in unsupervised domain adaptation setting. In addition, they present a novel method to induce domain invariant representations for a task in joint information extraction called domain adaptation for joint information extraction. So they propose an instance relational domain adaptation mechanism that seeks to align representations of task instances in joint information extraction across domains through a generalized version of domain adversarial learning approach. So the top figures demonstrate the difference between DANN and IRDA. Bottom figures are the relation graphs following the strict uniform alignment of standard domain adaptation methods. And C is the chain connection of IRDA. So this is the overall architecture. First, input sentences from both source and target domains go through the same in transformer encoder to compute their contextual representation. Concurrently, the CISL module extracts attention probability matrices at each layer to create attention graphs using position embedding as node features. These graphs are used to augment the dependency graphs, which are then focused across layers by GTN to create context invariant graph. The node features of which are combined with the contextual representation as input, for instance, span detection task using CRF layers. Next, the instance representations are computed based on the output that spans condition on the context invariant graph. Finally, source instances are used to optimize the encoder for the main tasks. So these are main tasks, and this is source flow data, target flow data, and joint. So these are source flow targets that goes to source flow. Finally, source instances are used to optimize the encoder. So it composes of 4 tasks: given an input sentence, a unified model, because one task is, for example, relation extraction, and the other task, all of them are related to each other. So in particular, it aims to detect and classify entity mentions, for example, EME, entity mentions extraction, according to set of predefined entity classes. For example, ETD, entity trigger detection. So it seeks to identify and classify event triggers. But event triggers can have multiple words. Then next, relation extraction objective is to predict the semantic relationship between the two entity mentions in the sentence. In unsupervised domain adaptation, data comes from two different domains. For training, we have a label source dataset consists of n sub number of samples and unlabeled set of n number of target samples drawn from target domain. The goal is to leverage both datasets to optimize model performance on test data from target domain. So, following this article, two conditional random field for event trigger and another for event mentions, taken as input word level contextual representation sequence, which is obtained by averaging the word pieces hidden vectors returned by transformer encoder. But the CRF output, the best begin internal output that tags a sequence that you know to indicate event trigger and entity mention event argument spans, which are then used to compute their representations. By aggregating information from words in the corresponding spans, finally, separate task-specific feed-forward networks are used to calculate label scores from these EAR, ETR because they are pair of entity mention spans, or these are, for example, pairs of entity mentions and event triggers in cross-entropy loss. So existing domain adaptation methods tend to view all domains equally and ignore any topological structure among different domains to align them all perfectly. So the vertex set V sub R, first we have a type relational graphs. The vertex set V sub R consists of 4 nodes. And the adjacency matrix dictates which pair of types should be aligned by setting the value of corresponding position to 1. We assume a chain connection in the respective mention order for G sub R. IRDA performs a minimax optimization similar to DANN. So it's a minimax, and lambda is just the balancing term here. So lambda S sub C is the combined loss for label prediction for joint information extraction in source domain, which depends on this encoder E and classification head F. So different from this model where the discriminator predicts the domain identity given representations in the domain, the discriminator objectives, this one, the second one, this is discriminator objective, aims to reconstruct the type relational graph given the encoding of data from different types. In particular, the graph discriminator computes the pairwise relationship between two instance representations for types I and j. And A sub ij is the value of edge between type I and j from adjacency matrix. A sub R. So D sub G aims to recover the relation graph via the adjacency structure, while E seeks to prevent it from doing so. At equilibrium, the representation of two connected types will provide no information regarding their connection. So these types are aligned as we cannot infer their origins based on their representations. One problem with domain adversarial training-based methods in general is that they are sensitive to amount of discrepancy between source and target domains. CISL first creates domain-independent structure by combining linguistic and attention graphs extracted from input sentence. So for linguistic graph, we employ dependency trees that prior work found to be useful for IE. So we have a graph, these vertices and this adjacency matrix is constructed for each sentence based on the output of the off-the-shelf, because you can use, for example, spaCy to just read off the dependency, and so you don't need to model the dependency parsing for yourself and train dependency parsing. You just use it off the shelf. Or you can use Stanford NLP, Core NLP, but it is in Java. So why not using spaCy? It's very fast. And then the adjacency matrix A sub D is a binary matrix whose cell is only set to 1 if W sub J is the governor of W sub I in the dependency tree. We create augmented versions of G sub D to reduce its sparsity and increase transferability by merging it with attention graphs extracted from the output of each layer of the transformer encoder. Specifically, we define an attention graph at layer L, which composes of transformers position embedding as node features for word level nodes, and attention probability matrix as adjacency matrix. So the resulting attention augmented dependency graphs are as follows. Because they are augmented, it's attention augmented dependency graph. So the alpha, beta are just learned weights that you should learn, and the z's are the node representation of the corresponding graphs. These graphs are context independent in the sense that no word embedding information is explicitly included in their node features, whereas the adjacency matrices reflects a relation among words that are universal across domains in natural language. Then this model employs graph transformer network to fuse the attention augmented dependency graphs. To incorporate G into instance representation learning, the only concern for me in this paper is that the computational complexity is huge. Otherwise, the idea is interesting, but the model should be simpler. So this is the F1 score of models of this simple data set, ACE. But it's a very simple data set. Even for this simple data set, you see the F1 score is pretty low for different models, for different tasks and different models. For different tasks, for different models. Task, trigger identification, role identification, entity, relation classification, trigger classification, argument role labeling, which is called role classifier. So 3, 4, 5, 6 tasks per model that you see comparison of their F1 score. This one is higher because it's simple, it's just entity detection. But the worst one is 49, which is for argument role labeling, because any trigger could be related to any entities, but the role is difficult to guess. It could be theme, for example, in biomedical text. It could be cause. But because in ACE we have more argument roles, so that's why it's more difficult in comparison for these labels. So each paper has its own limitations, with no exception. We present the first work to tackle the joint information extraction in unsupervised domain. Our framework combines instance relation domain adaptation with context invariant structured learning mechanism, outperforming state-of-the-art systems on ACE 25 and consistently across multiple new domains. Despite positive empirical results, there are still several limitations. First, the current model assumes a chain connection for a type relational graph. While intuitive and effective for the considered setting in this work, it is only design manual. Prior works have successfully improved using semantic role labeling and abstract meaning representation. Integrating structured graphs extracted from these methods is straightforward.